All right. We'll look at limits at infinity, and then also maybe a little bit of infinite limits here. Limits at infinity is kind of describing the end behavior. So perhaps you flatten out to some sort of asymptote, a horizontal asymptote, and then if you have a slant asymptote, then you're going to either shoot off to infinity or negative infinity. So to define a limit usually means we're going to a real number. So if I say the limit as x goes to infinity of f of x is L, where L is a finite real number, that means that we just need to get far enough out away from 0 on the right that the function will be very snug with a horizontal line at height L. It's going to get real close with an epsilon. So that means for every epsilon greater than 0, there exists an n, and we can use the natural numbers. You don't have to, but I decided to find it with the natural numbers, such that for all x greater than this natural number n, then the function and its limit is within epsilon. And then similarly for going to negative infinity, we have something very similar. For every epsilon greater than 0, there exists an m in the integers such that once x is less than m, then the distance between f of x and its limit is less than epsilon. So these are just meaning as I go to the left and the right, my function is going to flatten out to presumably some sort of horizontal asymptote. And it has to be some sort of asymptote at this point in time. All right, so I'm going to do an example with a reciprocal function to kind of illustrate this. We're going to show that the limit as x approaches infinity of 1 over x is equal to 0. So for our proof, we're going to let epsilon greater than 0 be given. Okay, and what I'm going to do is I'm going to choose, and here's where maybe it's not quite a natural number, but it works for real numbers too. So anyway, so we're going to let n equal 1 over epsilon. So if x is greater than 1 over epsilon, which is our n, then because epsilon's positive, 1 over epsilon's positive. Since x is larger than 1 over epsilon, x has to be positive also, which means we can multiply and divide the inequality without risk of dividing by a negative. So we don't have to flip the inequality. So epsilon is greater than 1 over x, which means 1 over x is small because epsilon can be as small as we want it to be. Thus, if x is further than n, this is going to imply that the distance between 1 over x and 0 is less than epsilon. And that's what we want to prove, that the limit as x goes to infinity of 1 over x is equal to 0. So to accompany this proof, we'll have a little bit of a picture here. At least I remember drawing a picture. Let's see. Similarly, we have some constant c over x to the k, where c is a real number, and k is some positive rational number. Then we also have that. So maybe I drew it in class. I thought I did draw it in class. Anyway, so I'm going to draw a picture for the reciprocal function. So we're just focused on the positive part right here. So there it is doing its thing. And let's say, here's my epsilon. So I want to be within epsilon of the x-axis. So we'd be, down here would be the minus epsilon. So we want to live within this tube. And so my n would just be there. So once my x gets past that, then your 1 over x is within epsilon of 0, and you can see that as we approach infinity, the graph is getting flatter and flatter as approaching 0, and that's what we're saying there. Okay. All right. So now we're going to look at another topic. It's limits at infinity. And what this should actually be is limits. We shouldn't say this. No. We should say infinite limits at infinity. And this just means that the function's unbounded. It's going to explode off to positive or negative infinity, or maybe even worse than that, all over the place. Well, if we're talking about a limit, then we will say that it's either going to positive or negative infinity. So the limit as x goes to infinity of f of x is equal to infinity. That means that for every big real number, there exists another real number such that if x is larger than this big number, then f of x is going to be larger than m. And this is the one that I thought I drew a picture of earlier. So here's our function in yellow here, and then m is some horizontal line, and it's just saying that any large number we pick, we can find an n such that any x beyond that is going to be above this line. All right. So let's find some limits, and there are corresponding ones for the limit as x goes to infinity, f of x goes to negative infinity, and also as x goes to negative infinity we have analogous. But I'm trying to make a short video here, so we're gonna do some examples now. Okay. So I'm going to find the limit as x goes to infinity of 5x cubed plus 1 over 10x cubed minus 3x squared plus 1, or plus 7, okay. And kind of what we were trying before is, we'd be approaching a number like 2, and first thing we do is try to directly substitute. Well, infinity is not a number, so we can't really directly substitute. And so it's kind of in what I would call indeterminate form. It's kind of like an infinity over infinity. So I don't know what that means, and so we're usually going to have to do some sort of trick, some algebra or something like that. And one of the common tricks is factoring out the highest exponent. So the highest exponent in both the numerator and the denominator is x cubed. So when we do that, we remove the 5's x cubed, and the 1 did not have an x cubed, so to compensate we're going to divide by x cubed, and we'll do kind of a similar thing in the denominator. So we took away the 10's x cubed, and the 3x squared, we had a square there, but we took away 3, so we need to compensate by dividing by x. And then the 7 didn't have anything, and to compensate we need to have 7 over x cubed. And now we're going to use that factor or result that if it's like some constant over an x to some positive rational power, then that's going to go off. As x goes to infinity, that's going to go to 0. Okay. So limit as x goes to infinity, the x cubes divide out, and you have 5 plus 1 over x cubed divided by 10 minus 3 over x plus 7 over x cubed. And so 1 over x cubed, if x cubed is like a million, then 1 over a million cubes can basically not going to contribute anything. Same thing with 3 over a million and 7 over a million cubed. Those aren't going to contribute anything, so we can essentially say that they go to 0. And in fact, they do go to 0. So what we're left is 5 over 10, which is also known as a half. So this one has a horizontal asymptote at 1/2. So in college algebra, you may have, and pre-cal, you probably looked at the degrees of a rational function. So the degree of the top is 3, the degree of the bottom is 3. So if we have a tie, it's the quotient. The horizontal asymptote is the quotient of the coefficients of the leading terms. Anyways, so we're going to do I don't know, a couple more. Get some good exciting examples in here. So let's look at this one. I got the fourth root of x to the fourth minus 1 all over x cubed. If I imagine infinity being plugged in, not really, but it's infinity over infinity, so that's indeterminate. So I'm going to have to do some sort of trick. And this trick is commonly used when we have some sort of root. And I notice I have a fourth power and a fourth root, so I'm going to do some sort of trick here. I'm going to factor out an x to the fourth, and I'll still have the fourth root. And then I'm going to be using this property right here. So if I have square root of a times b, it's the same thing as the square root of a times the square root of b. So we can break up radicals over a multiplication. So that's what's going to go on here. So I needed that multiplication. Okay. So this becomes the limit as x goes to infinity of just x. Normally it would be absolute value of x, but because x is going to infinity, we can safely assume that x is going to be positive, so we don't have to worry about the absolute value bars. So it'll just be x times fourth root of 1 minus 1 over x to the fourth divided by x cubed. Then it becomes limit as x goes to infinity. The x will cancel one of the x's in the denominator. Okay, so we have fourth root of 1 minus 1 over x to the fourth divided by x squared. And the 1 over x to the fourth, that's going to go to 0. And so we essentially have 1. So the fourth root of 1 is 1. So we essentially have 1 over x squared. What we can do is we can bound this function. We can bound this function. So the fourth root of 1 minus 1 over x to the fourth over x squared, that's going to be less than 1 over x squared. Since the 1 minus 1 over x to the fourth is going to be less than 1, and then we take the fourth root, it's still going to be a little bit less than 1. So we can bound that function by 1 over x squared, and 1 over x squared is certainly going to go to 0 as x goes to infinity if you want to be double sure. Okay. I got a couple more for you. So this one, you might want to practice a little bit to get the mechanics down, factoring out this power out of a radical. So let's do a limit as x approaches infinity of 5 over x minus x over 3. The 5 over x, 5 divided by a billion, really small. It's not contributing much. So as x gets very large, it's essentially 0. It goes to 0. And then x over 3, a million divided by 3 is still a lot. A trillion divided by 3 is still a lot. So I'm using this thought process of large numbers divided by 3 are still very large. So as x goes to infinity, x over 3 is going to go to infinity. And then I have that negative there that just makes it negative. So it's going to negative infinity. And then that's actually my slant asymptote. I got a slant asymptote at negative 1/3 x. Okay. Let's look at the limit as x goes to infinity of cosine of 1 over x. Again, that 1 over x is essentially going to 0. It's getting as small as we want. And pause the video. You all should know what the cosine of 0 is. I don't have to keep asking you. You should know this. It's 1. Okay. Alright, so I got one more good example for you. It looks kind of crazy when you first see it. So let's see what we got here. So we got the limit as x goes to infinity of 4x minus square root 16x squared minus x. And I'm going to say this is indeterminate form because if I imagine large numbers, 4 times a large number minus the square root of 16 times a large number squared minus a large number, I don't know what it is. I really don't. So we have to do some algebra. So one of the things to do with radicals oftentimes is to rationalize the numerator. That's a common trick. So we'll write this over 1, and then we'll rationalize it. So we'll multiply it by the conjugate which in effect changes it into a difference of squares. Okay, so it's going to be 4x squared minus 16x squared minus x quantity squared, which is minus 16x squared minus negative x becomes positive x. And then denominator, I did not forget my radical. We just put it in a little bit later. So the denominator is just going to be 4x plus square root of 16 minus x. So the 16x squared cancel out. We're just left with x upstairs, and we got 4x plus square root of 16 x squared minus x. And so what we're going to do here is we're skipping a little bit of steps here, but I'm going to do that same trick of factoring out because it's a square root. I want to factor out an x squared. So I'm going to factor out an x squared. And then again, we're going to infinity, so we can assume that the x is positive. So we factor out an x, so we got 4 plus. There would have been an x right here, but we factored it out. And then 16 minus 1 over, and that's not an x squared, it's just an x. I was just testing you guys. Okay, and so the x's are going to drop out. You're still going to have a 1 in the numerator, and now we can imagine a large number being placed in for x without getting infinity over infinity or infinity minus infinity plus infinity, because I don't know what all that means. It's crazy. Anyways, so that 1 over x. Oh, I'm testing you guys one more time here. It looks like. 1 over x, that's going to 0. And so really what we're left with is 4 plus square root of 16, which is 4, so we have an 8 in the denominator. Okay? And again, this technique will take a little bit of practice, but when we can't directly substitute or imagine large numbers, we have to do some sort of algebra. So in this case, infinity minus the square root of infinity minus infinity ended up being 1/8. So you really got to do the algebra, because I'm guessing it's not going to do.